This is Illustrative Math, Algebra 1, Unit 5, Lesson 4, Understanding Decay. Let's take a look at exponential decay. So the first activity is notice and wonder. You should pause the video, write down one thing you notice and one thing you wonder about these tables. All right, so you should have already noticed and wondered some things about these tables. Something I noticed looking at table A, as my x values increase by 1, my y values are increasing by 1.5 or 3/2. So if I were to graph this, it would look like a straight line with a positive slope of 3/2, and it looks like it would be passing through the y-axis at the point 0, 2. So this is a linear relationship in table A, and I know it's a linear relationship because it has a constant rate of change. For every one that we increase x, y is increasing 1.5 or 3/2. It's increasing at a constant rate. There isn't any variation in how much y increases or decreases for every equal one interval of x. But looking at table B, for every increase, we have an x for every single plus 1 in x, we are changing how much we increase y. First we go up by 1, 3 to 9/2. 9/2 is 4.5, so we're adding 1.5 or 3/2. From 9.5 to 9/2 to 27/4. 27/4 is the same as 6 3/4. So if we're going from 4.5 to 6 3/4, we're adding 2 1/4. So we're increasing as we are increasing x. We don't have a constant rate of increase here. We don't have a constant rate of change. It's increasing as it increases. So this is not going to be linear. Let me write down that as a notice. This is a linear relationship in table A, and table B is nonlinear. In fact, it would be exponential, because as I'm increasing my x value by the same interval as I'm going up by 1s, my y values are going to be increasing as the x values increase. So the change in y is increasing as the x values increase. So it's going to look something like this. It'll be an exponential relationship. And in fact, you might have noticed that just as we are adding 3/2 to our y values here in table A, we are actually multiplying each of our y values by 3/2 in table B. 2 times 3/2 is 3. 3 times 3/2 is 9/2. 9/2 times 3/2 is 27/4. And so we are multiplying by 3/2 as x increases by 1. If we are multiplying, then I know that it's going to be an exponential relationship here, because we're multiplying by powers of 3/2. One thing I wonder is what these different tables could represent, like what real life situation, or what's the context here, what's the relationship between these variables. All right, moving on to activity 2. What's left? Here's one way to think about how much Diego has left after spending a quarter of $100. Explain each step. So step 1, looks like we're starting with the $100, and then we are taking away a quarter of the $100, which represents the amount that he spent. So I'll just write in words what's happening here. Take away 1/4 of 100 from original amount of 100. Step 2, looks like we have factored out a 100 from both of the terms. So if we factor out 100 from 100, we'll be left with 1, right? 100 divided by 100 is 1. If we factor out a 100 from 1/4 times 100, we'll be left with 1/4, and that's what's happening in step 2. We have factored out 100, or divided both terms by 100. And we can do that because of the distributive property of multiplication. So another way to say factored out 100 from both terms is we divided both terms by 100. And then step 3 looks like we have distributed that 100. Not distributed that 100. We have simplified what's inside the parentheses. 1 minus 1/4 is 3/4. Simplified inside parentheses. And then the very last step is we have reversed the order of the multiplication, which we can do because of the commutative property of multiplication. So right here we've applied commutative property. Commutative property of multiplication and of addition means that you can think about the word commute. It means like to change positions. To commute to work, for example, is to drive, like like you're changing your physical position. So changing the physical position of these numbers, we will still get the same product because you can multiply numbers in any order and you'll still get the same product. So this is applying the commutative property, which we have for both multiplication and addition. So all we've done is reverse the order of these two factors. 100 times 3/4 is the same as 3/4 times 100. Okay, number 2, a person makes $1,800 per month, but a third of that amount goes to her rent. What two numbers can you multiply to find out how much she has after paying her rent? So if we think about what was just done here, to represent how much Diego has left, we're starting by representing the total amount and then taking away the amount that was spent, right? So start with the $1,800 and then take away how much her rent was. It was a third of $1,800. And then we can do the same thing that was applied in these steps in the first problem in order to change this term into, or change the entire expression into something similar, and use the laser pointer, to what we see here, where we are multiplying two numbers in order to represent the same amount. So the way we do that is by factoring out this 1,800 and then simplifying 1 minus 1/3. So you might think of it also as 1,800 minus a third of 1,800, you're going to be left with 2/3 of 1,800, right? So if her entire paycheck is $1,800 and we are using 1/3 of it for rent, what's going to be left? 2/3 of 1,800. It would be this amount here. So it makes sense that 2/3 of 1,800 is going to be the two numbers we multiply together. And just to see the calculations for why we can do that, let's follow the steps like we did here in problem 1 with number 2. So we're starting with 1,800, taking out a third of 1,800, subtracting a third of 1,800 to pay rent. This represents the rent amount. So I'm going to factor out 1,800. 1,800 divided by 1,800 is 1. And 1/3 times 1,800 divided by 1,800 leaves me with just 1/3. So I can see these two expressions are equivalent, right? Because all I did was divide both of these terms by 1,800. And I'm left with 1 minus 1/3 with 1,800 outside the parentheses. Now I can simplify what's inside the parentheses. 1 minus 1/3 is 2/3. I'll bring my work up here. So I'm left with 1,800 times 2/3. And just like it asked me to, we have found two numbers to multiply together to find out how much she has left after paying her rent. So after paying her rent, she will have 2/3 of $1,800 left. All right, on to the next. Oop, is that right? I think I'm missing a page here. Lesson 4. Looks like, here it is. All right, my pages were out of order, I apologize. Number 3, write an expression that only uses multiplication and that is equivalent to x reduced by 1/8 of x. So we're following the same process. We're starting with x, reducing it by 1/8 of x. We're going to factor out the common factor here, and what's common in both of these terms, x and 1/8 x, both have an x. So I can factor out the x, and I'll be left with x times 1 minus 1/8. Now I can simplify what's inside the parentheses. 1 minus 1/8 is 7/8. And I'm just going to rewrite it as 7/8 x because in math, we always write the coefficient before the variable. So this is an expression that only uses multiplication and is equivalent to x reduced by 1/2 x. Moving on, 4.3, value of a vehicle. Every year after a new car is purchased, it loses 1/3 of its value. Let's say that a new car costs $18,000. A buyer worries that the car will be worth nothing in 3 years. Do you agree? Explain your reasoning. So I would say no, it won't be worth nothing. It will be worth a lot less, but it can't be worth 0 because if we're constantly dividing by 3 or multiplying by 1/3, it's going to get very, very small, but it's not ever going to actually reach 0. It will approach 0. So I'll say no, it won't be worth 0. Because 1/3 of something is still something, no matter how small it is. It will approach 0, but it can't reach 0. The only time 1/3 of something will be 0 is if we're taking 1/3 of 0. All right, so another way to think about that, if we made a table, year and value, in year 1, it's worth, let's see, after 1 year, it's going to be worth 2/3 of 18,000 because it's lost 1/3 of its value. And then after a second year, it'll be worth 2/3 of that amount, 2/3 times 2/3 times 1,800. And then the third year, it's going to be worth 2/3 of year 2's amount. As you can see, we're working with powers again. Powers, oops, 18,000, 1,800. Okay. So here we have powers of 2/3. So we're actually going to do the same thing down in this table. Write an expression to show how to find the value of the car for each year listed in the table. So it says to write an expression, which is what I did up here. You can easily calculate, of course, and find out the actual value of the car after each of these years. You could divide the number by 3 or multiply by 1/3 to find out the value, or we can represent it with an expression. So year 0, the car is 18,000. And in year 1, it has lost 1/3 of its value, so it's worth 2/3 of its original value. And then in year 2, it's lost 2/3. I'm sorry, it's not lost 2/3. It's worth 2/3 of its value in year 1. And in year 3, it's worth 2/3 of its value in year 2. So let's review real quick. This is how much it's worth after year 1, because it's lost 1/3 of its value. It's worth 2/3 of 18,000. Here is that value again, but after year 2, it's lost another third, so it's only worth 2/3 of its year 1 value. And then here it is. It's after 2 years, it's worth this much. And in the third year, it loses another third, so we multiply by another 2/3 to tell its value. So as you can see, we are just multiplying by powers of 2/3, and if I counted them, 1, 2, 1, 2, 3, it matches how many years it's been. So I could represent this 2/3 instead of writing out so many. I can represent it with an exponent. So 2/3 to the 6th power times 18,000 will represent the value of the car in 6 years, and in t years, it will be worth 2/3 to the power of t times 18,000. 3, write an equation relating the value of the car in dollars V to the number of years t. So we're just going to use this expression that we just came up with here as the value of the value of the car after t years. So I'm just going to set that expression equal to V because it tells me to use V as the value of the car. So V equals 2/3 to the power of t times 18,000. And that equation relates the value of the car, V, to the number of years, t. Use your equation to find V when t is 0. What does this value of V mean in this situation? So if t is 0, that means year 0. And that's equal to 2/3 to the power of 0 times 1,800. And as we've seen in previous lessons, anything to the power of 0 is going to be 1. So this is just equal to 18,000, which makes sense because in year 0, when she gets the car is worth $18,000. So to explain what the value means, I need to write some words. It's the value of the car at year 0, or the time of purchase. Let me make sure that's a correct sentence here. The value of the car at year 0, time of purchase, is $18,000. Okay, let's move on. There is one more question for this problem, a different car loses value at a different rate. The value of this different car in dollars, D after t years, can be represented by the equation D equals 10,000 times 4/5 to the power of t. Explain what the numbers 10,000 and 4/5 mean in this situation. So just like we saw in the previous problem, the whole number that we were multiplying by the power represented the cost of the car in year 0, like the purchase price. So this car must have been bought for $10,000, and it's losing, this is how much it's worth after a given year, 4/5, so it must be losing 1/5 of its value each year. So 10,000 represents the purchase price of the car, and 4/5, and I'm going to say it loses 1/5 of its value each year. So 4/5 represents the retained value each year, basically how much value it retains each year. Four-fifths to the power of t would be how much of its value it has retained after t years. Okay, so there's an Are You Ready for More here, which we are going to skip, and then there's the lesson summary. So let's review real quick. Sometimes a quantity grows by the same factor at regular intervals. For example, population doubles every year. Sometimes a quantity decreases by the same factor at regular intervals. For example, a car might lose 1/3 of its value each year. Here's a situation that you can look at with a bacteria population that is decreasing by the same factor at regular intervals. So you can see if it starts at 100,000, we're going to be multiplying that 100,000 by some power each year. And the power is how much of its value or quantity is retained. So in this case, because the bacteria population loses 1/4 of its population each year, each day, then the remaining population is 3/4 of the previous population. So we'll be multiplying by a power of 3/4 each year. And then the power is determined by each day. The power is determined by the number of days. So this represents, this equation represents the population of the bacteria after D days. It's the original population times how much it retains after each day to the power of the number of days it's been. This is called a decay factor. So we've learned previously about the growth factor, which is how much it grows by. In this case, if we're losing value or losing population, which it'll typically be a fraction of the population remaining or a fraction of the value remaining, right? This represents the decay factor, and it's often a fraction. So we're done with lesson 4, and see you back for lesson 5.